Live from the North Carolina Museum of Natural Sciences in beautiful downtown Raleigh. It's the Science Cafe with your host, Brian Mallow.
Hello. Good evening. Welcome to the Daily Planet Cafe here in the Nature Research Center at the North Carolina Museum of Natural Sciences. And it's Thursday, which means it's Science Thursday. And this is our Science Cafe. Is anyone here for the first time? It looks like, are y'all here for the first time? Nope, okay, sorry. But we do have some new people here. Welcome. We do this every Thursday, although the first Thursday of each month is Science Trivia Night. So that's what's coming up next week is Science Trivia Night. And I forgot to ask Katie what cool cafes we have coming up next month, but I know we do have some cool ones.
Electric fish.
Electric fish? What's better than electric fish?
And veterinary medicine in our museum.
Oh, and we have veterinary medicine. So tonight's subject is in veterinary medicine, but we'll have one next month that involves our veterinary medicine right here. We have windows on animal health upstairs where people can watch veterinary procedures during the day. And it's not just a show because we happen to have a lot of animals here and they need taken care of. So tonight's program, as always, and for those of you that are new, the presentation will be about 20, 25 minutes or so, and the rest of our hour is Q&A. So we count on you to provide some of the programming here just by asking interesting questions. So when that comes, I'll bring a microphone around you because our programs stream live on YouTube and livestream.com, and they can be seen there later as well. So we do want to get everyone's questions into the microphone for that. So are you ready for our program tonight? We're kind of excited about it. We had a recent program about 3D printing that involved Matthew Fairber, one of our own staff members. And tonight's program is about a really interesting and I guess I won't say unique, but it's an extraordinarily rare collaboration and projects that are going on, although they've been going on already since at least 2002, so for about 13 years. It's coming out of NC State and the Center for Comparative Medicine and Translational Research, which involves a lot of cross-disciplinary collaborations, and that's what this one is about. So our guests, we actually have two guests tonight, and one is a veterinary orthopedic surgeon, and the other is an engineer. Specializing in 3D printing. And so I'm going to let them tell their story, and it's something they've been working on for quite a long time now and doing something really interesting that I've never heard about. So let's invite our guests to the stage. Ola Harrison and Denis Marcelin Little. Come on up. So, and just so you know, this is Ola, and he's the engineer, and this is Denis, and he's our veterinarian orthopedic surgeon, and take it away.
Thank you very much for that introduction. We're going to give you a little bit of an overview of some of the projects that we've been working on for a number of years now. So we've picked a few cases that we're going to show you just to give you an idea of what you can do with this fairly unique technology that we're using and that most people today call 3D printing.
Did you want to tell everyone your background in a few seconds?
So my background, I started out with my undergrad degree in mechanical engineering and then did my master and my PhD degree in industrial engineering, focusing on manufacturing. And so I'm coming from the design and the manufacturing side of this. And I've been involved in medical-related research since about 1996, I think, when I started working on orthopedic applications.
Good evening, everyone. So I am a veterinarian who has specialized to become a veterinary surgeon, and I've been working at NC State's vet school for about 25 years now as a veterinary surgeon, particularly a veterinary orthopedic surgeon. I stopped doing things other than orthopedics about 20 years ago or so. So we met, as you heard, in 2002. Ola had started at NC State in early 2002 and was reaching out to the vet school as a potential source of collaboration. And we'll hear the story in a second. I have a slides that shows kind of where we work now that we can go over briefly, and then I'll show you how we met in a second.
So we both belong to what is called the Center for Additive Manufacturing and Logistics, which is a research center at North Carolina State University. And this is the center, as you can see, so additive manufacturing is the other name for 3D printing. And within this center, we do a lot of different things. But so we're going to concentrate on the medical applications of these 3D printing technologies. But we do a lot of other things. But the middle thing there that is talking about finishing of metal AM parts, that's also part of the when we're making and designing and fabricating implants. So the 3D printing is just a first step, but for the final touch of these implants, we still need to use traditional processes as finished machining. And then the last part there is the design. So this is an important thing. 3D printing gives us a lot of design freedom. So we can now design and make parts that could never be made before. And we're taking full advantage of this for the implant side.
And you will see things shortly. So going back in time, we're now back in 2002, and the vet school has been a place for patients to be treated when they have limb deformities for a very long time. I've been very interested in managing deformities, and yes, in early 2002, this German Shepherd showed up, and you can see his legs are very deformed. He couldn't walk well. And there's something a little bit puzzling about his back legs is that they're both deformed, which generally suggests that there is a disease process, but generally there is more symmetry in the deformities. This dog looked very asymmetric. He looked a bit windswept. We see that in fall sometimes they have kind of a different deformities on each leg. It's very difficult as a veterinary orthopedic surgeon to assess deformities in the back leg, much more difficult than the front leg, especially around the femur, because there's a lot of muscles around it, and it usually has a very predictable way to get deformed, but this one didn't. So it was very fortuitous that Ola was just meeting with me within days of this dog arriving, and I talked to Ola. I say, I've got the situation to manage with 3D printing, so let's just do a CT scan of that dog. And here is actually a picture of that CT scan. Now, in 2002, our CTs, 2002, if you remember what kind of computers you were using or what a cell phone looked like, it was the same thing for a CT scan. Trying to do a CT scan of entire limbs in 2002 was a real challenge. In fact, it took 4 hours, and we had to do it twice. So it was very difficult at the time to be aiming to do this, but we took that CT, we managed to export the information, and I gave it to Ola, and a little bit later, this is what's happening. So tell us what we are looking at.
So we have a special software that we're using that can take these two-dimensional slice information from a CT or an MRI scanner, and through some editing, we can then create 3D computer models of the anatomy that we're interested in. So in this case, we're only interested in the bone anatomy. So from the CT scan, we could subtract out all the bony structures and create the 3D model in the computer. And then we use these 3D printing technologies to print out an exact replica of the entire lower body of this German Shepherd that we could use first to assess the deformities and then to plan the surgeries and also practice the surgeries.
Exactly, and that's what we did. And in fact, here is the kind of the real thing, if you want. This is called a ring fixator, which is a way to progressively correct or change the shape of a bone, make it longer, and correct angulation at the same time. So Bailey, that particular dog, had surgery on both legs, and we did the femur and the tibia. They were all deformed, if you want. but we could plan it so much better than we would otherwise plan. There is much less improvisation when we can rehearse a surgery. It was a bit of an effort at the time, and the process has been greatly simplified since then. In fact, we've done that particular thing several hundred times since then, but this was the first one that we did. The owner of Bailey had one goal. She had a Jeep, and she wanted Bailey to be able to jump into her Jeep. And, you know, a little bit after the bone were healed, the second surgery, Bailey was able to jump into the Jeep. We were very pleased with that. And often things come together in funny ways also. This owner didn't have the money. This particular process cost $6,000 back in 2002. And the owner didn't have the money, but she had a friend, a novelist, that had the money and gave her a check, wrote her a check for $6,000, and she, you know, a little bit of back and forth, and she finally accepted that check and made all this possible, and we've been building upon that. So that is a big area of medical 3D printing in orthopedics, would be to capture anatomy, generally from CT scans, sometimes from MRI, and analyze it or reproduce it. And we've been doing a lot of that along the way. We've done several graduate degrees. What you're looking at is a paper that involved making 153 replicas of a single bone, where we looked at the impact of the CT parameters. When you do a CT scan, you choose a lot of things, a lot of, you know, decisions have to be made about the voltage and the intensity and reconstruction parameters. And we've looked at how accurate our capture of the anatomy is for 3D printing purposes. We've also compared the precision, the reproducibility of different machines that we use for 3D printing, so we know how trustworthy they are when we make these replicas. And so we've been doing that for along the way, you know, a number of projects that worked that way. And you can see more recent deformity correction here. There is a replica of a front leg. We do many more front legs than back legs. And you can see here that we've made a replica. You want to tell us what kind of replica that is? And
So what you're looking at here was a replica of a very deformed forelimb from a basset hound. This is a very common deformity that you see in these smaller dogs. So we were printing, so this is made on a 3D printer called stereolithography, and that was the very, very first 3D printing technology that was ever developed. And that happened around 1986, the first machine came out, and I think they sold their first machine in 1987, and that's a US company called 3D Systems. And they're still one of the largest companies in the world within the 3D printing industry.
so we're using these replicas. I usually have a couple made. One is going to be used as a reference even during surgery, and the other one is used to rehearse a surgery. We could make more if we need them. And they're, you know, the price is, they're not super cheap. The SLA ones will cost a few $100s, but we don't like to waste money. And these days, you know, the cost of 3D printing is going down. The precision of 3D printing is okay, and you know, I think the cost of usable replicas of bone is getting lower and lower by the month, if you want. So here, this type of surgical rehearsal actually has allowed us to make new surgeries, to be a bit more aggressive in correcting deformities. The frame that you're looking at has 2 sets of hinges within a very short bone, and that's really only possible because we can build these frames with great confidence, because we know that we're doing surgery on the leg before we're really doing it on the dog. So you can see actually that particular patient with these radiographs. They look a bit like, you know, it's very predictable because, you know, we've been rehearsing it. So it's been tempting, as far as 3D printing goes, to say, well, you know, I can build complicated things. The interesting aspect of 3D printers is that they'll build layers by layers, and a 3D printer doesn't worry about how complicated or complex a structure that's built. So it's been very attractive to try to build implants that are 3D printed. So the picture that you show is actually a plate. The pink plate has been designed on a femur of a young dog. And you want to talk about it?
So the problem with the standard off-the-shelf implants that are used normally is that the surgeon actually spends a lot of time during surgery to try to shape it to fit the shape of the bone of this patient. So the whole idea here is that with these 3D computer models that we have, we can custom design these plates in advance. And the first couple of cases that we did, we printed them in metal. That's the material that is normally used. In this case, the pink plate that you see there is actually going over the growth plate. And so as Denis mentioned, this is a young dog. And if you're putting a metal plate over a growth plate, then you're going to restrict the growth of that bone. And so what you really need to do is to go in and remove that plate after that fracture is healed. But that's a second surgery. There's more complication that can happen. So we were looking for a way of creating a plate that would actually disappear over time. So if you have a plate that would last only for, let's say, 10 weeks, the bone has a chance to heal, but then the plate itself would disappear in the body.
So, and that's what we are exploring with this particular project. We were comparing these somewhat 3D printed. What we do is we 3D print a mold, and then we injection mold a bioresorbable plate, and then we can use these plates. We were doing a mechanical project where we compared different thickness of resorbable plates. We have a handful of polymers that are biocompatible that we can rely on. And that's a kind of a very futuristic way to look at implants, but it's obviously in our best interest sometimes to have implants that kind of melt away with time, and 3D printing may play a role in doing these types of implants. We also wanted to push the envelope further, and we have been able to do that with the arrival along the way of a metal 3D printing. Ola is going to talk about this a little.
So when we started out in 2002, all the 3D printers that were around were polymer based. There were a few that could use some kind of ceramic materials, but they were not very strong parts. There have been some attempts to develop metal 3D printers, but they were based on a technology that ended up with very porous metal parts that were not very strong. So they worked for prototyping purposes, but you couldn't make parts that you were really going to use. In 2002, there was a company named Arcam that had been working for about 7 years to develop the first metal printer in the world that could make fully dense metal parts. And we actually bought the very, very first machine that was ever sold in the world. So that machine came to NC State early 2003. At that time, the only material that was available was steel, because they really had developed this 3D printer to make tools. So as part of this purchase, we said, if we're going to buy this machine, you need to develop titanium, because we really want to be able to print implants. So the company, that was not their intention, but they agreed to do this. And today, about half of all their machines are now used to make implants.
And the other half?
The other half is basically used for aerospace applications. So those are the two main areas.
And none of them, interestingly, is being used for the original purpose that they designed the machines for. So along the way, we've seen a number of patients that, again, are coming to the vet school generally with pretty big problems. And then we've been able, with an acceleration in imaging, we can do CTs, by the way, these days in about 30 seconds that are more precise than the CTs we were doing in 4 hours in 2002. We can export information much more readily. We have a hardware link between the vet school and engineering, where we can automatically transfer our studies. We can upload. The software is much more effective. And the fabrication methods have improved significantly. So I'm showing you a patient that arrived a few years ago that has cancer in his femur. his thigh bone, had cancer, and that cancer was controlled using radiation therapy. In fact, that's the first cat that underwent that form of radiation therapy with a linear accelerator, and that took place at Colorado State University. Very special kitty that goes around the country for his therapy. So he had radiation therapy at Colorado State, but unfortunately, this is what his femur looked like at the end of radiation. His femur is basically dead because it was filled with tumor, and the tumor was killed by the radiation. So he was very painful in his knee. His knee was basically falling apart, and we didn't really have any option for management. We had to 3D print something. So we designed it. This is easier said than done. It's not a small task. It took about 15 people with different expertise to kind of lend a hand, if you want, on some aspect of that design. So we have, it's not even a regular total knee, it's a custom total knee, a limb-sparing total knee that is called a mobile bearing knee in some way. That's a knee that has a little bit of freedom of movement between the different components. You see a metal, a plastic, and then a metal part. And that is what we plan to build, and we built using 3D printing. So it would be extremely difficult, in fact impossible, to build an implant of that nature without 3D printing. And it was very hard to do even with our years of experience in 3D printing, because this implant has bearing surfaces that are extremely smooth. It has textured surfaces that allow for bone ingrowth. On right underneath, you'll see maybe a tiny bit of a layer at the edge that the bone will grow into. It has rigid portion that go up the shaft of that dead bone. It has locking bolts that are very precisely fitting with that implant, and that is a very complex thing to be doing that can only happen with 3D printing.
I think this was, when we did this was the first time that anybody had made a knee implant of this size. So this is, as far as we know, the smallest knee implant that has ever been made. And it was custom, and it was as complex and as fancy as any human knee implant that exists today.
And so here is the implant in place. That surgery was a success. It made a big, positive impact on Cyrano, the cat that you saw in that picture. And so that was another big step forward in kind of collaborating with each other, opening the door to free-form, 3D printed total joints that can be used for limb sparing. I'll show you another kitty while we are looking at cats, and this one showed up a little earlier, and he was missing both of his back feet. So we have potentially the option to build socket prosthesis, just like any amputee would use if they had reasonably long stumps, and if they didn't have too much skin mobility. But for, first, cats don't like too much to be constrained, as you've probably figured out. If you try to put your cat in some garment of some kind, they often feel very unhappy. Or if you place something on their leg, they can shake at ultrasonic speed. It's very dangerous to see a cat shake at super high speed. And so this cat had a lot of mobility of his skin in relation to the little residual bones that he had, and socket prostheses were not an option. So we decided to explore another strategy for this cat, and we were particularly motivated by the fact that he was not doing well at all because he was missing both of his back feet. So we happened to be co-teaching a course at that time. You want to tell us about this?
So we have a course that we call the biomodeling course, and it's basically a course in how to use 3D printing technologies for medical applications. And so in this course, we've been teaching this course since 2005, and the students have to do a project, and they have to develop something during the semester. So this year we had 2 students that were given this challenge to design a new type of an prosthetic device. So in this case, we're looking for a prosthetics that will be connected directly to the bone, and for the bone to grow into it, so the prosthetic actually becomes part of the bone and not being a loose prosthetic that you can take off.
And we weren't the first one to be thinking about this type of implants. In fact, it started in Sweden. Sweden has a long tradition of orthopedic research, in basic research, and in the 50s, osseointegration was discovered in Sweden, and or first reported in Sweden, and by a gentleman named Brannemark, who was a dental surgeon, a dentist, doing basic research. And about 30 years later, his son, who is an orthopedic surgeon, also Swedish, decided to try to potentially place an implant inside the bone. So that happened in the 80s. It's been kind of low numbers of people, both in Sweden, a little bit in the UK, that have had this transdermal osseointegrated implant. And shortly before we saw this cat, another kind of being exposed to something, another veterinarian who was finishing his career at the Ohio State University, Marvin Olmsted, had actually tried to place an implant through the skin of a cat. They were not 3D printed implants. They were very, very kind of crude in their design, and the surgery was very invasive. And I thought, ooh, I mean, the idea is interesting, but the concept is kind of brutal. But maybe we can make that a little bit more sophisticated, much less invasive, safer, by using 3D printing. And so that's what you see right there. You see a replica of the leg that's kind of stops mid-tibia, the shin bone. And then you see the implant that's been 3D printed that will be adapted to the size of the bone. That was the first one we did. And so it looks very simple. And here is what it looked like when we were done with surgery right there. Looks a bit futuristic. And that area of research is another thing that might be growing. It has grown a lot in complexity and scope over the years. So I have a picture of something a bit more recent here that you'll see is much more sophisticated, is more freeform, and is adapted to this time the front leg of a bigger dog. And so you can see that a few years later our implants are more sophisticated but still rely on 3D printing. And here is what that surgery would look like when we're done with it on the dog. And I have a picture of that dog when he received his first foot. That was a trial foot, and you can see we relied on a very high-tech engineered tennis ball right there. My wife, who actually is on the back of the room there, told me that she's not an engineer, but she knows a lot of things. And she told me that this would never be a success because when the dog went to the park, every other dog would chase the dog's leg. But so I pursued this just to prove her wrong. So it was very, as you can see, that ball is moving way too fast for any dog to pay any attention to it. So, but it shows you this is obviously a very serious business, you wouldn't tell, but where we potentially can make this process is by no means completely established. It's very investigative, but again, 3D printing has allowed us to create implants that are much more tailored to what we do, that have maybe layers that can be added to these implants to reattach specific structures or to protect against infection. And our work is kind of continuing in that area.
And we have done, I think, about 15 cases. So the two first ones were cats that we did, but after that, they've all been dogs, and mostly of them large dogs. And we've had a lot of successes. We did one dog that actually had both back legs missing. So we did a bilateral, and he went from not be able to walk to run. And over the years, we've been contacted multiple times by veterans. They're from the VA, so people coming back from the war that lost a limb, and today are using the external prosthetics, the traditional socket prosthetics, and when they see this, they all go, we want this too, when can we get it? So our goal is to sometime in the future to, even here in the United States, to be able to translate this into the human medicine.
So you can see the range of patients that we manage, and our lab relies on a lot of equipment. I have some pictures of that equipment here that Ola can talk about also.
So what you see here, these are all what we call low-end polymer printers. These are 3D printers that usually cost less than $5,000, and that's very cheap for a 3D printer. And we have a lot of these in our lab, but they're mostly used for teaching purposes of our students, but also for early prototyping. Then here you see some of the higher end machines. So these are a lot more expensive, but they're faster, they're more accurate. They're the one up there on the right hand corner is one of the first printers on the market now that can do composites. So you can actually print parts with carbon fiber, Kevlar fibers, and so on, and make parts that are very, very strong and stiff out of these polymers. The other is the metal side. So as we described earlier, the gray machine up here, that was the very first metal 3D printer in the world that could do fully dense metal parts. And the way that these machines work is that they spread a thin layer of the metal powder, and the two top machines there, they use an electron beam to selectively melt one layer of that metal. And then you lower your build table, you spread a new layer of metal powder, and you print the next or melt the next layer on top of that. So this is an additive process where you add layers of materials. And so basically you take your CAD model and you slice that CAD model into two-dimensional cross sections, and then we build them back up one by one on top of the other. So it's kind of like when you're building a tall building. You start with the first floor, then you build your second floor, your third floor, and so on until the building is complete. So the two top machines there are based on the electron beam melting process, and then the white one in the left lower corner there is the same process, but is using a laser instead of an electron beam. And the big difference here is that the laser can be focused much better. So when you're making very small implant with a lot of details, the laser process is preferred over the electron beam. So another printer that you see here is what is called a 3D bioplotter. And this is a 3D printer that has been designed specifically for tissue engineering applications. So in this case, you can still print, like you can see the structures here, we can print scaffolds that are made out of different types of biopolymers. So these are polymers that are biocompatible, but they're also bioresorbable. So they disappear over time inside the body. But what is unique with this printer that instead of just be able to print the polymers, you can also print cells, you can print proteins, you can print growth factors. So the idea here is that you're actually printing an entire scaffold with the cells in its place where you want them, and you can print multiple types of cells. So now you have a construct that you can put into an incubator, and within days or weeks, it turns into a piece of tissue. So the holy grail with this technology is that sometime in the future that we will be able to print replacement organs using these type of technologies.
That's literally an ear. So that's actually, is that distinguishable from an ear cut off a cadaver, for example?
So what you see there is that that's the scaffold where the cells are inside. And then as the cell starts to create, it's what we call the extracellular matrix, that polymer starts to dissolve, and eventually it is completely replaced by real tissue.
We also realized along the way that finishing implants is a very complicated business. The manufacturers have worked really, really hard on getting these things to be perfect the way they are. They generally don't share all their information with you. I can understand why. It's a pretty secretive universe, but we've been working our way towards the fabrication of structures using machines, and we've added to our suite very sophisticated machines that allow us to build either finish our structure. By finishing, I mean making them, choosing the texture, the surface roughness that we want, making sure that things are exactly the way we want with regard to size. It's very complicated from an engineering perspective, but also building the little parts that go with our custom implant. We sometimes will need custom locking bolts, and that are made of cobalt chromium. That's another metal that we work with for custom total joints a lot. And it's not so easy to find a little custom bolt made of cobalt chromium. So we've been very fortunate to add to our lab several machines. Ola, you want to tell us what they are, maybe?
So these are very high-end CNC milling and turning machines and grinding machines. And these are the exact same type of machines that the implant companies are using today. Normally, they will start out with a big block of metal, and then they will start to machine away to shape the implant, and they will then have to come back and grind the surfaces. So with this equipment, we can 3D print very complex geometries, but then with this equipment, we can then come in and do the finishing and get the same type of surfaces that you see on off-the-shelf implants. With this, since all these processes that we're using are based on, or they're using the metal powders as their stock material, we have to have a lot of equipment that goes with this that we use to characterize that powder, because the shape and the size of those powder particles are very, very important. So there's a lot of equipment that comes around that we need when we're doing this type of research. And of course, if you're making implants, you want to make sure that these implants are going to be strong enough. So we have to do a lot of testing on these, especially if it's a load-bearing implant. If you're looking at the human hip implants or knee implants, they need to pass a test of 10 million cycles. So we have this type of equipment so that we can do our own fatigue testing on these structures to make sure that they're going to be strong enough.
And so you can see here a little bit of the summary of what we do. You have a CT scan. The image gets into a computer. We use CAD to kind of capture that bone in that case. We manipulate it in the computer, smooth it. We then design the implant, the portion that we want to replace or add. We fine-tune that design. It gets exported into other software that will be fed into the 3D printer, and it gets 3D printed and finished at the end. And so that's telling you in a nutshell why we've been collaborating for 13 years. You can see that's both crazy and exciting, if you want. It's a very complicated process, but things are accelerating. We're a bit like the Borg. Every time we do something, we sweat a lot, and then we struggle, and then we achieve something, and then the next time things go a lot faster, and we can say, well, what's the next thing on our wish list? And that's basically what we've been doing for 13 years. Thank you, everyone. We are happy to take questions now.
Thank you very much. Nice round of applause for Ola Harrison and Denis Marcellin-Little. And yes, so now the rest of our program will be Q&A, and I just ask that you get my attention, and I'll bring the microphone around to you. And does anyone have a question that would like to start us off? I'll bring this over to you.
It's really, really amazing. You said several times that you were doing things with the additive process that could not be done otherwise. And I'm just wondering if you could explain a little more why these things could not be done by a machining, taking away process.
So there were some of these that show some pretty intricate structures. One thing that we can do with these machines that was hard to see on some of these images, that we can even make like mesh structures. So we can create textures on a surface that is perfect for bone ingrowth that you can't make with regular processes. There are so tiny features that it will be impossible to do it through traditional machining. So they're also, when you're when you're machining something, you always need a line of sight anywhere that your tool is going to be able to remove material. So there is limitations on the geometries that you can create because of that. But since we're building this up layer by layer, the machine doesn't care about the complexity of that geometry.
And I'll add that when something is built commercially, it's based on a process, as you can imagine. People don't start building plates just for the heck of it. They'll just say, well, we're going to build 5 sizes and 6 lengths, and then we're going to have a certain plate that goes with a certain number of tools. And so if you are a bit of a tweener, if you are between sizes, or your bone is too long or too narrow or too this or too that, then you are out of luck. But with this, we can merge maybe our implants with something. We can use the tools of a specific system, but make an implant that's unique to that. So it has expanded application, just like we would do a transdermal implant. We might use bolts that are commercial bolts, but our implant will be unique for that patient. Or our plate, we've done plates that were unique also in shape or size or length. Total joints can be unique also. Doing a new total joint would cost a lot of money, and so here we can actually have a small series or an N of one, just one total joint that fits a specific geometry, because for us it doesn't cost a lot more to just do one.
And also that very often in orthopedics, since you have these off-the-shelf implants that are usually designed for the average person, and the average person doesn't really exist. So the surgeon has to try to fit the patient's bone to the implant. But with the process that we have, we fit the implant to the patient's bone. Yep.
What are the long-term outcomes of these procedures? Like, 5 years, 10 years, and so forth. I realize when you're working with dogs and cats, 15 years is probably longer than the patient is going to survive.
So there are actually, recently, there are a couple of companies now in the world that are actually using these 3D printing technologies to mass produce implants. And there are a few that are doing customized, but they are even finding that these technologies are cheaper in many ways to do even the standard implants. And when you're talking about a hip implant for a human patient, they're talking about 20, 25 years, hopefully, that is going to last. And they've done testing to show that that is feasible.
And I'll add that there are standard ways to assess, the longevity of implants, and these implants are going to play by the same rules as other implants. They also, for example, once bone ingrowth occurs into a cementless cup, for example, then the implant is relatively protected. It's all can be broken down into how the body is dealing with something, how the bone is growing into it, and how strong it is in the short term. And those rules are well known, so the 3D printed implants are going to play by the same rules as the regular implants.
You make me somewhat curious. I do have an artificial shoulder. I'm an average person, the doctor thought. So is this going to be a short thing? This was just one that he showed me. You saw off the top of the bone, you stick a spoon in it, and that's the end of that. Why do you talk so much about the customization of the implant, whereas, believe me, this is standard, and I'm standard 6'1", that's it.
So obviously not every patient is going to need a customized implant, but there are a lot of cases out there where they're basically trying to find the best implant that they can to fit this patient, but it's still not a perfect fit. And they have to do a lot of cutting and trying to mediate during the surgery to get the best result that they can with what is available. And these type of patients could really benefit from these customized implants. There are also a whole area of, like, when you're talking about like for head and neck injuries and cranial reconstructions, there are no standard implants. And all those implants today are done partially before the surgery, but then during the surgery, they have to do a lot of adjustments to them to make them fit that patient. And those are things that we today can customize and print, and they know that they're going to fit when they come into the surgery.
So you talked about vets approaching you about possibility of having access to some of these kinds of technologies. Is the way this works that most of the research happens first in animals and then eventually transfers over to humans, or is there research taking place in parallel for both kinds of patients?
Sometimes it's done in parallel. One good example, I think, is that one thing that is becoming very popular these days that are using more and more is robotic surgery. And that was actually something that was developed by a veterinarian surgeon. So they started using robotic surgeries in animals before they translated it into human. So sometimes it starts primarily in the vet side, but then there are times where there's parallel development going on.
And it's not unusual for researchers to be adjunct in different environments or to collaborate or have joint projects. So for us, there's a lot of synergy with limb sparing, maybe at UNC and Duke and elsewhere. So we'll have specific applications that say, well, and again, we would have to tackle things that are otherwise impossible. You know, we can't strategically dislodge something that's 98% successful. It would not make any strategic sense. We would say, well, what's the worst that's going to happen about your shoulder? It would be, oh, you have a cancer or something failed 3 times. So we usually have to prove our worth by tackling the most difficult things. And again, 3D printing is the right thing for that because it doesn't care how complicated things are. And so that's what we will be doing, you know, and we'll say, well, what's the worst in limb sparing, or how might you do transdermal osseointegration? So, for example, we're doing research at UNC that's funded by the National Science Foundation that's looking at maybe different strategies for transdermal implants that would either rely on 3D printing or not rely on 3D printing, and you know, all that is of benefits for people in the future.
I think you answered some of my question, but it's a little bit about the art in the design part. Like, for example, if you saw something, do you have to resist from trying to make it better?
Well, I mean, the design part here is really is a very multidisciplinary thing. So we have engineering teams, we have students that are working with us from different backgrounds in engineering, and they might come up with an initial design. But from that stage is really an interaction. So it's going back and forth with the surgeons are looking at it and say, well, I would like to change this. I want this to be a little bit more curved over here. I want more coverage on this area. And so these are not implants that we just design in a day and print them out. We usually go back and forth for several weeks. And then we print out these plastic models and we practice the surgery on there. And then the surgeon will look at this and say, well, this was, it's okay, but if we can add this, it will make it easier, it will make it more secure, and so on.
Yeah. And philosophically, I think, you know, maybe we're doing these things for the first time because we are driven to, you know, make things better or make them happen for the first time. But, you know, once you've done something once or twice, or you got to do it a little bit better, I think it's genetic, maybe.
Can you talk a little bit more about the testing that has to be done before you actually put an implant into an animal, or, you know, I assume in the future in a human? Because, I mean, with, like, say, a shoulder implant like he has, you would assume that a bunch of those would be made. You'd be able to destructively test that.
Yeah.
Do you do the same with one-off implant?
We don't, for one-off implants, we don't test them to failure. We do start out with printing test specimens that we run through these fatigue tests. And these are tests that it might take several months where you're trying to reach the 10 million cycles. And so we're doing geometries that are similar that has been 3D printed and not the exact implant, but you're testing the structure and the material in itself, making sure that you're getting the right properties. When we're printing an implant, we also print test specimens around it that we can evaluate, and making sure that we don't have any defects within the parts that are printed around it. And that gives us a pretty good confidence that the implant is going to be fine as well.
And our group, I think, plays a role not just in applying some of these things clinically, but also in working on the parameters that might optimize 3D printing in the future, or increasing our trust into the long-term performance of these implants. That is the kind of the basic research that's going on. That's pre-medical, if you want. On the medical side, all these things are still very investigative, and they are, they're not the cheapest. It's going to cost several $1,000s to do these implants. It's not, and sometimes we do research. We look for funds in different sources, and we're not picky. We'll take it from anywhere. We'll have funds from donations. We'll have funds from grants. We'll have funds from internal budgets. We move. We work hard in making things happen, but it's still, it's still investigative at this point.
I've seen all of the total knee replacements that you've designed on the computers and then printed out, but I was wondering if you had yet worked with the engineering department to design some more complex total joint replacements, like in wrists or ankles.
That's a good question, and we are very interested in the concept of hemiarthroplasty, where you don't have to do a total joint that is very aggressive, in a sense that requires removing the bone on both sides of the total joints. Ideally, I'm thinking total joints sometimes are needed in patients that have a fairly normal cartilage on one side, and we are doing a lot of work on trying to improve the precision of what we build, and working with different materials also that are 3D printed directly or indirectly, like those resorbable plates you saw. We want to make implants precise enough that they can articulate with cartilage over the long term, and that's a big area of research that will be growing in the future. So yes, we're very interested in how precise our implants are, how to improve that precision. We're doing a lot of research in that area, and we are designing several joints that are going to be taking advantage of that, or helping us test the precision of what we're doing. I can't talk about exactly what, because sometimes in research you got to keep a secret or two, but we can talk after the conference.
It seems like when your implants are so precisely manufactured, it would cut down on the time it takes to do a surgery. Can you speak to whether that is happening, and give us an example of how long it might have taken the old way and how long it takes this way?
So that's an excellent point, an excellent question. When we talk about improving performance, so sometimes we make something impossible possible. That's pretty objective, basically, because often we agree on what's impossible if you are in the field. But also we would want to make things either last longer, or you could say, well, what do these implants do? Sometimes we design implants that are less stiff, so they merge with the bone. So we've done research, and then we measure the effort that the bone has to do to hold that implant while it's loaded. So that's one objective measure of an impact on the bone. We also measure how precise our surgeries are. So then we'll 3D print maybe specific guides. We did that a while ago, and we could improve the precision of what we were doing about tenfold, which makes sense. If things are planned with a machine, they're going to be better off than conventional. We also measure the increased stability of the construct that we do. And to do that, we've designed bones that are 3D printed that actually are as solid as bones, not just a pretty replica, but we've been optimizing our blend of epoxy and short glass fibers to make bonds that are as solid as bone. That's a big area of that we're working on. And so now we test these constructs with 3D printed implants or not, and we improve the strength of fabrication by about 30%. And we also accelerate surgeries. We tested that in a specific surgery, and we could also accelerate surgery by about 30%. So as we know, the length of surgery is greatly influences a lot of things, including infection rate and time. Altogether is cost. And so, yes, we can make things faster measurably with these methods.
So you were talking about how, I guess, the first metal printer was available in 2002 and how everything has really evolved since then. I was kind of wondering, where do you see things evolving to, like maybe in the next 5 to 10 years?
It's a good question, and we get that question quite often. There are already some hospitals that are looking at investing in these type of equipment. So now it does take a big team to make this work, but there are some people that have the vision that in the future you might have this set up at a hospital, and you will basically design and print your own implants, and you can do it on demand. So you can get a patient come in, you get the CT scan, you might spend a week to do a design, fabricate the implant and get it ready, and then a week later they can come back and get their custom implant. So it is not that far-fetched. I mean, we can do this with a patient today. We're a little bit cautious, so we probably spend more time than we need. We usually take maybe 3-4 weeks from the design till we have the final implant. But that's also something that we're working on trying to streamline. So the first implants we do took several months, and now we're down to a couple of weeks. And we think that with more design of the streamlining, we can get that down to a couple of days.
Ola and Denis, this has been fantastic, and we're about out of time. We have time for one more question. So here we go.
Well, I already took one. Does somebody else want to?
Oh, no. Do you have one there? All right.
So what lies between the animal implants and the human implants? What has to happen before it becomes practice on people?
So there's something that is called FDA, and right now they're what's in between. These machines have actually been FDA approved. That means that you can print a standard implant. So if you're using the same material and the same design that are used for off-the-shelf, they're approved by FDA. But and you can do that, and there are companies that do that today. But the real strength is if you can make these custom implants, and FDA is still a little bit iffy about that. And of course, the big implant companies are interested in these technologies. They're already using it, but they can't really release this until FDA has given their blessing.
And we're going to squeeze in one more question.
So once everything is designed, how long does it take to actually print an implant?
That's another good question. So, of course, it depends very much on the size. As small, we've made some implants for Chihuahuas. They only take maybe 5 or 6 hours to print the implant, and you're going to spend more time doing the finishing than it took to print them. A larger implant, you might look at something like 10, 15, or 20 hours to print. But with these machines, in most cases, you wouldn't just print one. So if you're really in the business of making custom implants, you will fill the whole chamber, and you might print 20 different implants at the same time to really get the economy. So now you start a machine, and it might run for 30, 40 hours, but you have 20 implants when that build is done.
Excellent. Well, thank you very much. How about a nice round of applause for Denis and Ola. And I think if you still have some more questions, I'm sure the doors are locked and they can't leave that quickly, so you'll still have a chance to speak with them. Our own next week is Science Trivia Night, and next month we have our own veterinarians doing a program, and we have a program on electric fish. And in December, we're going to be doing something for the first time, which is a science spelling bee, which sort of similar to Trivia Night, you can participate. There will be teams. Katie, do you want to say something there?
And there'll be prizes.
There are prizes. That changes everything. So, and there will be teams, and a single representative from each team will come up and participate. So, Science Spelling Bee. One more time for our guests. Thank you very much. And this building is still open till 9 o'clock, so you don't actually have to leave yet. Thank you very much, and we'll see you next time.